Why do so many cosmic metronome signals still come out half a beat off, even after we correct for redshift and every textbook effect we know? In the energy filament theory, those stubborn frequency shifts are not random noise or messy environments. They are the echoes of particles using an older timing standard when the signal was born, written into the universe as an era-dependent offset in the beat itself. Astronomers rely on a few famous cosmic clocks, the 21 centimeter line from hydrogen, which should sit at a very specific radio frequency once redshift is removed. The lighthouse flashes of pulsars whose spin periods are modeled down to tiny fractions of a second, and the breathing brightness cycles of some quasars, tied to regular motion in their plasma disks. For each of these, theory gives you a clean should-be value. You then divide out the overall redshift from expansion and expect the remaining frequencies to match the model. What observers actually see is that, after you pull out redshift, the peak still sits a little to one side. Not wildly, but by a small, stable, directionally consistent amount. And that same kind of offset shows up again and again in different objects. The standard move is to point at complexity, gas clouds, tangled magnetic fields, velocity gradients, internal turbulence, plus the limitations of telescopes and data pipelines. All of those are real and they certainly blur things. The puzzle is that as data improves, some of these little offsets refuse to wash out and start to look less like random dirt on the lens and more like a faint but consistent pattern in the music. In this picture, the key step is to treat all these signals as what they really are, beating systems. The 21 centimeter line comes from a tiny flip in the hydrogen electron-proton spin configuration. A pulsar's tick comes from the whole star's rotation and the way its internal particle soup carries angular momentum and fields. A quasar's heartbeat comes from matter swirling and crashing near a giant black hole in repeating cycles. None of these frequencies are arbitrary. They are the natural tempos that particles and structures choose in a given tension environment. Close to Earth, we've already seen that particle timing is not rigid. Electrons change their rhythm enough that atomic clocks drift with altitude and speed. Fragile structures like positronium live for slightly different times in different media and others. Particles answer changes in tension with small shifts in size, lifetime, or magnetism. On cosmic scales, the same rule applies. The punchline is simple. The particles that emitted those ancient signals were playing with the version of their own rhythm that existed in that era of the energy sea. And we are trying to line them up with the updated rhythm built into our particles today. When we say they are off by a bit, what we are really measuring is a difference in version, not a distortion added later. It sounds abstract. Think of it like listening to a live concert recording from decades ago with a modern digital tuner in your hand. Back then, the tuning standards, the instruments, and the recording chain were all slightly different. The singer is not singing out of tune, they are singing in tune with that older standard. When you check every note against today's exact pitch, you find a small, systematic offset and it shows up on every track. In this view, redshift is like playing the whole concert slower and lower, while frequency anomalies are like discovering that the band's metronome was itself set a little differently in that era. The hydrogen line, the pulsar flash, and the quasar rhythm are all honest. They are simply locked to the particle structures and tension fields that existed at the time of emission. We subtract the big, geometric part of the story expansion, but we do not subtract the fact that the underlying instruments have changed since then. So redshift becomes the large-scale error difference in energy. Spectral line distortions become the error difference in internal structure, and these frequency anomalies are the error difference in the beats that whole systems use to keep time. Together they say the same thing the rest of this season has been saying from different angles. The tension of the energy sea has been evolving, and particles have quietly evolved with it, leaving timestamps in light, in chemistry, in nuclear yields, and now in the timing of entire stars and galaxies. In the next episode we'll pull all these clues onto one map from atomic clocks, proton size and neutron lifetime to positronium, electron magnetism, spectral drift, molecular rulers, lithium shortfalls, and these frequency shifts and See how they fit into one continuous evidence chain for particle evolution. Tap follow, share it on New Physics, Clear Universe.